I want to put you in the shoes of one of our customers when they were operating MirrorMaker 2, and they saw this screen coming out of the consumer offsets tool. So the consumer offsets tool, it's a script that you can use to monitor what consumer groups you have in your cluster and what they're doing. And we'll see if anybody has used this before. Does anybody see anything strange? You can shout it out as soon as you see it. Sorry? The negative lag, exactly. The consumer lag is negative. We seem to have a consumer group that has time traveled and is reading messages that haven't even been written yet. And this is not good. I mean, it looks a little bit silly, but it maybe looks harmless. And in reality, this is hiding a very, very serious bug that we need to resolve. So we're going to go on a quest to try and fix this bug. How hard could it be? 1 minus sign. And in order to do that, I need to take you through sort of how MirrorMaker 2 works, what is actually causing that negative lag, all of the things that we thought about, ways to try and fix that, what we ended up landing on and merging into Apache Kafka, and why that solution is still sort of not good enough. So, what is MirrorMaker 2? I think I've selected myself for all the MirrorMaker 2 experts, but for anybody that isn't, it's a tool for replicating data between Kafka clusters. The idea being that if you have data in one cluster, it does very good internal replication. But when you need that data in another cluster, you need to pick up a tool like MirrorMaker. It's been included in every Kafka release since 2.4. And the reason it's 2 is because MirrorMaker 1 is now deprecated and being removed in 4.0. So if you still haven't migrated, please do. It's based on the Kafka Connect framework, so it sort of runs as a persistent service. And it has no cute animal mascot, like some of the other systems that we have presentations here at Current. So I will just be representing it as a blank white box. This is a more sort of detailed diagram of how MirrorMaker 2 is working. The two biggest pieces here are the mirror source task and the mirror checkpoint task. And these two have different responsibilities in MirrorMaker 2. The mirror source task is primarily concerned with data replication that happens between the source and target topics. And this is exactly what you want in data replication. You need something to move the data. The mirror source task does that. As a byproduct of replicating this data, the mirror source task will emit offset syncs to an offset sync topic, recording where certain destination offsets in the destination topic came from in the source topic. That data is picked up by the mirror checkpoint task, which is working on offsets replication or consumer group syncing. The idea here is that even if you replicate your data, you still want to replicate your consumer groups to remember where in that data you've already read. This is a critical part of any sort of disaster recovery plan. You don't want to, after failing over to your target cluster, reprocess weeks, months, or years of data. And this offsets replication uses data from two different sources here, the source topic and the source group, via this offset syncs topic. And it operates in parallel to the mirror source task at all times. And finally, as a sort of side effect of the mirror checkpoint task's operation, it'll produce checkpoint records to a checkpoint topic. And this is basically saying, for a specific consumer group, I did offsets translation, I synced it across, and this is the sort of pair that I have. And diving in one more level deeper, just so that we have a basis for understanding the rest of the talk. This is how I'm going to be representing offset syncs. In the top of the slide, you can see that we have sort of source records in a source topic. There are these arrows drawn between this and the target topic. And in this example, we have a total of 2,000 records in the source topic. We have 1,000 records in the destination topic that MirrorMaker 2 wrote there. And we have two offset syncs. The first one on the left is at 0, sort of at the very beginning of the topic, and the next one is at 500, for example. Each of these offset sinks consists of a topic partition. So this is specific to a pair of records, a pair of topic partitions. And it consists of an upstream offset and a downstream offset. When you have a reprocessing happening in MirrorMaker 2, because it fails just like anything else, you can end up with data being rewritten. And in this case, you have new offset sinks written for that data to record where it landed. So in general, you have a many-to-many relationship between these offset sinks, or offset sinks between the two different topic partitions. And this presents a lot of challenges because you can't really know a lot about the topic from a single offset sink. Information is very local to the specific record that it is recording the translation for. So these sorts of diagrams I'm going to be using a lot. So let me know if you have any confusion afterwards. So let's talk about legacy offsets translation, how we did it in the before times, more than a year ago. So the idea here is that we can get away with storing very few offset sinks. So in this case, a single offset sink for thousands and thousands of records. And we can perform addition and subtraction on offsets to sort of compute a relative distance between records in the topics. So in this example, we have a consumer group here up at the top in the 2000 block of records. And we want to do translation of that to the target topic. So we can do translation by going back from the consumer group to the offset sink that is closest. Then we go forward that same distance in the target topic, and we end up with a consumer group in the target topic. And if this consumer group were to move forward in the topic later, and a new offset sync happens, and we have data redelivered, we can then perform translation based on a different offset sync, but use the same strategy of subtraction and addition in order to find the destination consumer group. So in reality, in practice, replication has lag. So in this case, we're looking at a MirrorMaker 2 flow that has only replicated 2,000 records out of the total 5,000 in the topic. And the consumer group is fairly far along in the topic. It's existed longer than MirrorMaker 2. This would be the situation if you were taking an existing workload and trying to migrate it with MirrorMaker 2. MirrorMaker 2 is going to start at some point in the past and catch up. And in this situation, if we use that addition and subtraction strategy, we're going to end up with negative lag, our problem child. You can see the reason that it's negative is that the amount that we've added has surpassed the end of the topic partition. It has included records that have not yet been replicated. Now, if this were to continue normally, if we didn't have any failures in MirrorMaker 2, we would eventually write the 3,000 and the 4,000 block, and everything would be fine. And this is sort of the assumption that we made in the initial version, that this would be sufficient. But if we consider that in practice, topics have gaps in them, they're not contiguous blocks of records. These gaps can come from, most notably in my situation, exactly once transaction markers. These are basically offsets in the topic that exist, and they count for offsets. They count for offsets, they count for consumer groups, but they aren't actually records that get delivered to your application. And most importantly for that, they can't be replicated by MirrorMaker 2 because we're using sort of stock producers and consumers. Other sources of gaps are compacted records. So if you have a compacted topic and you have an older version of a key, Kafka has the feature where you can remove that data because it's no longer relevant. And this just leaves gaps in your topic. It doesn't move around offsets. Similarly, for deleted records, if stuff falls off the end of the topic. And a more contrived situation is if you're filtering records as you're mirroring them, which is theoretically a feature that MirrorMaker 2 has. Those records that you're filtering out appear as gaps. So when you're replicating a topic with gaps, those gaps are removed, and the negative lag can still appear, same way it did before. But if we then try and catch up, complete the replication, we end up in this situation where data loss has occurred. And this is why the negative lag is so dangerous. So in this situation, the addition has added past the gaps in the source topic, and has essentially made it so that the number of records you skipped all appear as records that don't ultimately get delivered when you do a failover. And the way you can see this in this diagram is that in the source partition, that block of red records is ahead of the consumer group, meaning the source consumer has not yet delivered and committed them. But in the target topic, they are behind the consumer group, meaning that it appears as if the target consumer group has committed them. And if you were to do a failover in this situation, the source consumer group says, I haven't yet delivered it. The target says, I have delivered it. And so in practice, nobody delivers it. So it functions as data loss. Most importantly, the thing is that the data replication has proceeded normally. The data actually is there in the topic. It's just when you use consumer groups that the failover does not deliver all of the data. So what does this mean for our delivery guarantees and our replication semantics? I'm borrowing this term from lower level networking. We have essentially best effort offsets replication. That means anything goes. The data could get there, it could not. It might be delivered multiple times, who knows? And that's not okay. I know my title says that's okay. This part is not okay. I think that in the Kafka community, it's sort of a baseline expectation that delivery is at least once. Because if you weren't getting at least once delivery, why are you using Kafka? You could just send your data over UDP. And like I said earlier, this is even in the situation where data replication still has at least once guarantees. We never dropped any data in reality. It's just that when we did this specific failover with offsets, we got this best effort semantics. Okay, so the customer comes to me with this, and they look at that, and they're like, this is not good enough. Best effort is not good enough, and we need to fix it. So how do we go about fixing this problem? The most important thing that we need to remove is this addition, because the addition is putting us past data that either hasn't been replicated yet or will never be replicated. So we can only really commit offsets for stuff that has actually been replicated. So one way to do this, so in this case, if we remove addition from our subtract, move over, and add process, the arrow, instead of sort of being a C shape, looks like this L shape, or I don't know. I didn't figure out what letter that was. The idea is that you find your closest offset sync, and you use it for translation, but then you don't try and go forward in time. You don't try and move past records that you think will be replicated, because the offset sync just tells you all of the stuff that has been replicated. It doesn't tell you anything about the future. And this is technically enough to avoid data loss. But if we just did this, and this actually was my first PR, if you do this, you end up with all kinds of other problems, because by default, MirrorMaker 2 emitted very few syncs because it didn't think it needed very many. And in order to replicate the same sort of behaviors that MirrorMaker 2 had, we need a lot of syncs. You can imagine in the most extreme case, we need a sync for every single record. Now, I haven't drawn that. Each block of 1,000 records has an offset sync about every 100 records, so we have 10 times or 100 times as less offset syncs. And even this amount is just absurd. To talk about how absurd it is, I want to sort of talk through the diagram. Some of the details I left out of the architecture diagram earlier are sort of related to where the data actually lives. And in practice, the offset sync topic, the data is stored on a Kafka broker on a hard drive or even an SSD. It's transported over a network to the mirror checkpoint task where it's actually loaded into memory. And in this strategy of storing every offset sync, we blow our memory budget like instantly. It's so bad that if we were to store 1 bit of data in memory for every offset that could be in a topic, that turns out to be over an exabyte of data, which I don't work in supercomputers, and I don't suggest that you use Connect on a supercomputer. But I don't know any computers that have an exabyte of RAM. And they certainly wouldn't be running Kafka Connect. So we can't fit that many offset syncs in memory. That's kind of a silly thing to even think. But the sort of more practical lesson here is that we don't want our memory usage to scale with how much data we have stored. That would be bad architecture, so we can't do it. So storing every offset sync is out. We have to store fewer. The next natural thing to talk about is to try and avoid storing all of that data in memory and rely on our persistent storage in Kafka to read it to us on demand. And based on the way that consumers work, they're very well optimized for linearly reading blocks of data. And so we can use a strategy where we don't load all of the data into memory, but we have a consumer that's continuously reading beginning to end. And as a block of offset syncs comes into memory, you can use it to do offset translation, and then throw it away immediately afterwards, knowing that eventually you'll read it back from the topic. And using that same diagram before, this is a similarly absurd solution because of that poor network in between. I don't know if anyone has read sort of a blog post about using the network as a file system. It's a very, very bad idea because those poor routers in between only have a limited amount of memory, and stuff is getting faster and faster. And so a network is not a place to store an exabyte of data. So this one's out. We can't do this one. We could try and store less data in memory, but only try and load it once. So we don't abuse our network or our memory. And the sort of most obvious way to do that is to implement a FIFO cache. So the idea being that as you get a new sync, which is this dashed line at the end of the topic, you expire the oldest sync that is farthest back in the topic. So first in, first out. The downside here is not so much an architectural problem, but the fact that it doesn't provide any translation for everything that's been expired. And in practical terms, if we're trying to make like reasonable memory savings here, if you stored 10,000 records that allow you to do offset translation for a budget of about 100 megs or so, but you have like millions of records in your topic, you're doing translation for like 0.1% of your topic, which just is not really good enough. And it's not good enough in sort of an interesting way for me as a maintainer of Kafka, because we need to target sort of the lowest common denominator, a solution that works for everyone. So despite it providing really good translation at the end of the topic, the costs are really too much for us. It does not provide any translation for groups with high consumer lag, which some people might expect MirrorMaker to be able to do. We need to choose a fixed cache size that works for everyone. Originally, we were trying to do this as a bug fix, so that you don't have a turn off leaky data, don't turn off data loss bug configuration in Kafka. So we need to choose a fixed cache size that works for everyone. If we made it 100, it wouldn't work for certain people. If we made it 1,000,000, it wouldn't work for certain people, because different people have different memory budgets, different people have different topic sizes and throughputs, And so we couldn't find a sort of one-size-fits-all solution for them. And I guess the takeaway that I have from this solution is that it really makes inefficient use of memory. We store a lot of sinks very close together that provide really good translation, but each marginal record that we store there really close together is kind of low value. And so we could make very much more strategic use of that memory if we were to remember older records. So with that intro, how do we do it now? I call this the sparse cache. So as opposed to the dense cache of storing lots of records close together, we just store a few records, but in strategic locations. So here I have a very minimal diagram because it's only a 5,000 topic, 5,000 record topic. But the idea is here that we store these sinks in a strategic way, which I've found to be an exponential cache. So what I mean here is that the spacing between the offset sinks that we're storing is an approximate doubling of each adjacent sink. So you can see those two offset sinks that are very close to the end of the topic, they're only 100 records apart. So you get very good translation right there. And the next pair of records are 200 records apart, 400 records apart. My largest labeled here is 1,600, but it could get larger and larger for longer and longer topics. And then we also try and store one record at the very beginning of the topic to sort of cover up the back end. And if we do this exponential shaped cache, we end up with 64 of these sinks to cover an entire Kafka topic. 64 because offsets are a long, which has 64 bits. And so if you double your data, basically each sink ends up covering 1 bit of your offset numbers. And it's kind of a weird cache to wrap my head around at first. I sort of kept trying to write it backwards, where I store offset 1, but not 2, 3, but not 4, 5, 6, so on and so forth. The fact that it is oriented towards the end of the topic, where the offsets are higher, is really important to provide a good translation of the offsets. So in order to do offsets translation in this environment, we do the same sort of strategy as the other caches, where we find the closest sink and translate against it. So you can see this offset, or this consumer group that's in the 4,000 block, sort of early in the 4,000 block, it gets offset back to the 2,000 block. When this consumer group moves forward, in this example, it moves into the 5,000 block, very close to the end of the topic. It gets translated somewhere else in the 5,000 block. And effectively, you can see here that the consumer group that's older, that's farther back in the topic, it got worse translation because the spacing was larger. But as it gets closer to the end of the topic, as its lag is lower, and especially once it gets to the end of the topic, you can get very, very good translation. So exponential, like I said, the really cool thing for us was that it is self-tuning to any workload size. So because everybody's using 64-bit offsets, 64 bits is enough for everybody. 64 bits is enough for our cache. It prioritizes translation for low lag groups, which is a benefit of the FIFO cache. And it has low precision translation for these high lag groups, so that it provides some amount of translation even if you're very far back in the topic. And it has this very low fixed memory usage per partition. So 64 offset sinks is like a kilobyte of data. So you could have hundreds of thousands of partitions potentially, and it doesn't really break anybody's memory budget. And the cool property that I found afterwards is that output consumer lag is about double the input consumer lag. So in this example, the consumer group has about 2,000 lag. It's translated relative to an offset that's about 4,000 offsets back in the topic, and it's about double. And if I did the same example earlier in the topic or later in the topic, the property still holds. So how do you actually build a cache that is denser at the end and doesn't actually act like a binary number at the beginning? It involves expiring syncs that are too close together. And in order to realize what too close together actually means in a strong sense, you have to go read the code. Unfortunately, I didn't have time to include that in this presentation. And in this example here, instead of the oldest offset sync in the cache being expired, we pick this offset sync that's in the middle of the cache, because the new sync coming in has made it so that we have sort of 4 syncs that are all 100 records apart. And so we don't need that second red arrow to actually perform translation. It's now too close to the other offsets. Just for anybody that reads the code later, this sort of notion of too close, it gets farther apart and more generous as you move farther back in the topic. So we could even expire one of the very old syncs in the topic, assuming that it was old enough farther back from the end of the topic. So here, if we did that and expired data that was relatively old in the topic, it's very likely that we performed translation using it. So here in this example, we have a consumer group that used this red offset sync to do translation. But the offset sync is too close together. We've got 4 consecutive offset syncs that are about 800 apart, I think, in this example. And so once you actually expire that, the consumer group was still translated in the past. That state still exists. And you'll then do translation based on an earlier offset sync. And so if you just applied this cache, you would basically, as the offset's translation proceeded, even if your consumer group didn't move on the source, it would appear to go backwards on the target. Now, this is a bug that never actually released because we sort of knew about it immediately. But it requires some additional state to filter out these sort of backwards syncs, or these backwards moving translations. And it's very simple to remember sort of that orange arrow, remember where you did translation in the past, and just do a very simple comparison to filter these out. But it caused us problems later because that data that we needed to filter out these sort of backwards syncs was being lost during restarts. So remember from the architecture diagram, the mirror checkpoint task is actually a process in memory. It had a little in-memory cache of previous translations it had done, and it would lose that cache. It would forget when a restart happened. So we fixed that part of the bug in version 3.8 by rereading the checkpoint topic, basically looking back in the history of our translations to find out where did we translate it to in the past, and reloading that data basically into memory. And this was important for us to fix, and is a reason I would strongly discourage using version 3.5 through 3.7, because after you have a restart of the mirror checkpoint task, you would have lots of unavailability of translation. You would sort of have it forget all of its past translations. So rather than your translation being offline for the minute or so it took for the checkpoint task to restart, you could be losing weeks of translation. So a very important fix. So don't use 3.5 through 3.7. So the sort of lesson that I have here is that offset translation is better now, but it's still not very good. Oh, I said bad. Offset translation is still bad. To explain sort of how bad it is, I want to take you through the offset translation funnel. I always see like salespeople talk about funnels here, engineering funnel. At the top of the funnel, we have your actual replicated data. This is your actual data that's providing value to your users. And there is a massive number of these. In this example, it's 1.8 E19. That's, I think, more than a billion, so a lot of zeros. And theoretically, based on if you have optimal translation and things go really well, that is reduced by a factor of 100 to the next layer of the funnel. So we'll replicate a billion records, but we'll only store 100th of them as offset sinks. That sort of factor of 100 is just a default. You can configure it. And so you can get more offset sinks to sort of broaden that part of the funnel. Now, the crazy part of the funnel is the green layer of the offset sinks in memory. Remember that we have a very low memory budget compared to our disk budget. And so rather than storing n or a linear amount of offset sinks, we're storing a logarithmic amount. And the logarithmic function is really crazy. It takes a billion or 100th of a billion and crushes it down to 64. So if this funnel were to scale, the top two would be across the entire screen, and you wouldn't even have a single pixel associated with that green layer. And there's even more layers of sort of poor translation. If you have 64 offset sinks in memory, which is sort of the ideal case, only the ones that are older than your consumer group are relevant for translation. All of the stuff that's newer is relevant for newer consumer groups that have lower lag, but you can only use stuff that's older. And finally, once you look in the cache and figure out which one is going to do your offset translation, you're down to one offset. One offset out of the initial billion offsets in your topic was actually used for translation. And what this means in practice is that the precision of this process, the precision of the answer that it gives you at the end is very low. And that's sort of the summary I have for all of the algorithms that we discussed today, is that we originally came trying to improve the accuracy of the system. So if you have data loss, if the translation was wrong and it caused you to lose data, you're not accurate. So our legacy strategy is not accurate. If you try and store every sink using a dense cache, you blow your memory budget. You got your accuracy back, because now we have the accuracy check. We lost our memory check. If we do the rereading sinks topic, we blow our I/O usage metric. It's just an untenable amount of data transfer. If we implement the sparse cache from versions 3.5 to through 3.7, we get the memory and I/O usage, but we sort of have lost availability because there are portions of the topic that we can't do translation for. And finally, if we have the sparse topic, the sparse cache plus the restoration strategy that we implemented in 3.8, we get our availability back because you're able to translate stuff that's very old in the offset sinks topic. But one of the properties that the legacy strategy had that none of the strategies that we've discussed so far have is precision. It's something that we gave up and never got back. So the legacy strategy, when it was doing addition and subtraction, it could add down to a single offset. And so if your offset in the source moved forward by 1, offset in the destination could move forward by 1. And none of the strategies that I've presented so far to fix the original correctness bug offer that same precision. And that's really what you need to be aware of when you're using MirrorMaker 2, even in the latest versions. So revisiting our replication semantics, we've managed to take offsets replication from best effort to at least once, meaning we don't drop data when you're using offsets that have been replicated by MirrorMaker. And coincidentally, the data replication became exactly once for a completely different reason. KIP 618 was exactly once source connectors, and in Kafka 3.5 and above, MirrorMaker 2 offers exactly once data translation, or data replication. It makes sure that if you have one record in your source and you read committed on the target topic, you'll only get one record in the destination. But if you combine that exactly once system with offsets replication, it's still only exactly once. We can't make the guarantee that if you commit data on the source cluster, that it won't be redelivered on the target cluster. But we will guarantee that it will arrive at least once, which is the whole effort that I've been on over the past year. So just some notes for operators and sort of summarizing what we've learned. Offset translation is perfect at the end of the topic. So if you're able to get your consumer groups to commit very close to the end of the topic or at the end of the topic, you can expect sort of minimal redelivery once you do a failover. Those offsets that are mid-topic have approximately double the lag that they did in the source cluster. So if you're not able to get your consumers to really sync up all the way, you should definitely expect some redelivery, even in the perfect cases. I mentioned offset lag max as a way that we sort of filter out a whole bunch of offset syncs. By default, it's 100, which is not good for certain workloads. So if you have very small topics that have very low amounts of data in them, it can be useful to lower this number so that more stuff ends up in that second layer of the funnel, and so more stuff is available for later layers. The throughput on this is getting into some internal details if you dig deeper. The throughput on the offset syncs topic is, or can be, a very extreme bottleneck. So if you have 100 topic partitions being replicated by MirrorMaker 2, that's all great and parallelizable, but there's only one partition in the offset syncs topic. So if you're expecting to write one offset sync for every record, you turn your offset lag max down very low, you're just going to end up with problems on your offset syncs topic. So I have a couple strategies for dealing with that. And finally, the 3.8 fix that I mentioned of reading the checkpoint topic, it requires write credentials for the actual offset syncs topic, which is traditionally not something that was necessary. So if you see some of these log messages, just be aware that you may still be in that 3.5 to 3.7 sort of poor restart behavior mode. So overall, I would say that I've benefited MirrorMaker 2 a certain amount in fixing our accuracy problem, but I've created new problems because engineering is just a system of trade-offs. And I think that we can continue to make MirrorMaker 2 better. So if you have ideas on ways to fix it, please get involved. And if you're interested in sort of what the next generation of MirrorMaker 2 could be, if you're interested, we have a kip out for cross-cluster replication, which I'm looking for contributors for. So if you're interested in helping out MirrorMaker 2 in the open source, please consider contributing to Kafka. I have a link to the contributing section, and also these slides. So thank you so much for listening. I hope that you've learned something about MirrorMaker 2, and you're able to make it work well in your situation with proper tuning. And so thank you very much.